Good morning. Today I will briefly again uh, review linear block codes. We started with linear block codes yesterday, but I will review and I will then explain further decoding and how to generate the codes. Now, this is the diagram of a digital communication system in which this channel coding part. So, from at the transmitter, you do the channel coding, and at the receiver, you perform the channel decoding. Rest, I have already explained this diagram, right? And I have also covered what is channel coding. Channel coding is actually transforming signals to improve communication performance by increasing the robustness against channel impairments like noise, interference, fading, etc. So basically, the channel will introduce noise to the signal, and channel coding is done to mitigate the effects of noise. All right. Then this is the coding gain that we will achieve. This G is the coding gain that we will achieve if we transmit the data in the coded form, and this EV by N0 is the signal to noise ratio for the uncoded signal, and EV by N0, minus EV by N0, this is the signal to noise ratio for the coded signal. So clearly, from this graph also it is clear that for uncoded signals, the signal to noise ratio requirements is more as compared to the coded signal. So we will achieve a coding gain, which is the difference of the two signal to noise ratios, the uncoded signal and the coded signal, right? Then I started with uh, describing the channel coding, and in that some basic concepts were there, like binary field. We will only discuss about the binary field only. I will describe when I will describe the linear block codes, we will consider only the binary set in which there can be two elements only, 0 and 1, which can be transmitted. And these are some operations which can be performed on the elements of the binary field, 0 and 1. So addition is there and the multiplication is there. And this binary field is also called the Galois field, and it is represented like GF. In the bracket it is 2 because there are only two elements in the alphabet. Alphabet means only one of the two elements can be transmitted and received at the receiver. Then these are some basic fundamentals regarding the fields. It has to be commutative. Uh, it has to, fulfill the commutative property. Then associate distributive property, so etc. I think I have already discussed these things. Now, what is the vector space? Vector space is, for example, how do you represent a linear block code? Okay, a linear block code is represented with n comma k. N is the number of bits in the code word, and k are the message bits. Right? K by n is the code rate, is defined as the code rate, and 2 raised to the power n will be the elements, will be the complete vector space, right? 2 raised to the power k are the combinations for the message bits. If there are 2 bits, there can be 2 to the power 2. There can be 4 combinations in which the input bits can come. And if let's say it is and n is the number of bits in the code word. So what we have to basically do is we have to code the message block into the code word. So code word will definitely have more bits as compared to the message block. N is always greater than k, because n will have certain parity bits which can be used to detect and correct the errors. All right. Then let me come back to display. So vector space is 2 raised to the power n. So all the elements of the code word which can be there is actually the vector space. For example, if I take the case of V4 means n is equal to 4. So there will be 16 possible combinations, right? And let us say I'm taking 2 bits at a time. So I need 4 code words out of this, because what are the combinations of the input bits? 0, 0, 0, 1, 1, 0, and 1, 1. So 2-bit combinations. I need 4 code words from V4 from the vector space. So those 4 code words will be called as the subspace, right? Now a subset S of the vector space Vn is called a subspace if I will have to take the all zeros vector, I will have to consider the all zeros vector, and the rest of the vectors will be the sum of any 2 vectors in S. That subspace, that space will be called as a subspace in which the 2 vectors, once you add the 2 vectors, add means you do the modulo addition. Modulo addition means if you do a, if you are doing the bitwise XORing. So the result of the sum of the 2 vectors should also be in the subspace. So that is the condition to form a subspace basically. All right, and this second property is called the closure property. Then what happens is that instead of k bits are there at the input, n bits are there at the output of the channel encoder block, right? So 2 raised to the power k combinations will be there at the input and 2 raised to the power n combinations will be there at the output. Now what happens is that once the values of n and k go very large, maybe let's say n is equal to 150 and k is equal to 50. So in that case, the combinations at the input and the output will be huge. So it is very difficult to do the one-to-one mapping of the message block with the code word using a lookup table. So if certain combination of bits come, I should be able to pick the code word from the code book or the lookup table. But it will be very difficult if the values of n and k will be very large. In that case, what I will do is that I will pick only k rather than 2 raised to the power k. I will pick only k components, right? Let me just explain this point. Okay, from the generating set. So instead of taking, so Vk is the set, Vk is actually 2 raised to the power k, Vn is actually 2 raised to the power n. So I need how many code words? I need 2 raised to the power k code words out of 2 raised to the power n, right? But if the values of n and k are very large, in that case, it will be very difficult to store these code words in a lookup table. So rather than storing the lookup, storing the code words, the mapping between the input message block and the code word, rather than storing it in the form of a lookup table, what I will do is that I will generate every time when the message bits come, I will generate the code word rather than picking it from the lookup table. How can I generate? Rather than considering 2 raised to the power k message blocks, I will consider only k code words. Out of this, I will consider only k code words, right? And I will construct a matrix which is called the generating matrix, right? So these code words v1, v2 up to vk. So v1 will have how many elements? It is a vector. It's a row vector. It will have n elements. Similarly, v2 will have n elements. Vk will also have n elements. Now, what should be the? How should I construct the generating matrix? So I will take those k vectors which are linearly independent, and this set of k vectors which will be used to generate the code word. These set of k vectors are called the basis of the code book, right? So and how many elements are there in the generating matrix? How many elements are there? How many vectors are there in the generating matrix? That is known as the dimension of the generating matrix, right? Number of elements will be equal to the dimension of the generating matrix, and these vectors will be linearly independent. No vector from these k vectors can be formed with a linear combination of any vector, right? So that is linear independence. The point is that rather than doing the mapping of the, rather than storing the code words, how many code words? 2 raised to the power k code words out of this 2 raised to the power n, because my message block is k bits. So how many combinations are possible? 2 raised to the power k. How many, when certain combination comes, how many code words I require from this vector space? 2 raised to the power k. So there has to be a one-to-one mapping right? Rather than storing the values in the lookup table, I say that you generate the code word every time. So how do you generate? How do you generate the code words? You take k vectors, k code words, right? You take the k code words as generating matrix. The limitation on these k code words is that they will have to be linearly independent, right? And this is called the basis of the generating set, basis of the code, the code book, or the code book, or the code book and code, designing a code or designing a code book, uh, uh, I mean, reflect the same thing. So this is the k vectors are called the basis of the generating matrix, and number of elements will be called as the dimension of the generating matrix, right? So how the code words will be generated? This is generating matrix. When the message bits come, right, there can be k message bits. So this is also a matrix v1 v2 up to vk, right? So these, there will be matrix multiplication, and then you will get the code word generated corresponding to this combination of message bits which have come at the input. So the rows of G are linearly independent, as I have already explained. So this is my G, right? This is my M. M is a row vector. I will multiply the row vector with this matrix to get the code word corresponding to this message vector. This formula explains the multiplication or matrix multiplication basically. For example, now I have taken an example here where generating matrix, this is some generating matrix. Now from this generating matrix, it is clear that what is the value of M. I can take it straight away from this generating matrix, because in one row there are 6 elements. So 6 elements means n is equal to 6. And how many rows are there in this generating matrix? 3 rows are there. 3 rows are there. So that means k is equal to 3. So this is the generating matrix for what linear block code? 6, 3. Because n is equal to 6 and k is equal to 3. So if, let us say, this message vector comes, right, and I will multiply this message vector with this generating matrix. If you multiply, so this will be the code word generated, 101110 correspond. So what is the meaning? When 110 will come at the input of the channel coder block, what will happen is the from the transmitter, actually it is not 110 that will be transmitted, but it is this code that will be transmitted, 101110, right? So we will add some amount of redundancy so that if any bits go in error, I should be able to detect and correct the errors. So that's the basic goal. These are the message vectors. Using this generating matrix, I can generate the code word set, right? Because I know what is the generating matrix, I know the message vector, I can get the code word by multiplying the message vector with the generating matrix. Then what is the systematic block code? So in the systematic block code, what will happen? This is the code word 11010. This is one of the code word. So some portion of the code word will have the information bits only. For example, if you look at this code word 100, so 100 is the message vector. 010 is again a message vector. So this message vector is a part of the code word. So that will be called as the systematic block code. For a systematic code, the first or last, as I said yesterday, I will consider only the last, but you can consider the first also. There can be examples where the first k bits will be message bits in the code word, but let us consider k message bits at the last as message bits in the code word. So for a systematic code, the first k elements in the first or last k elements in the code word are information bits. So if that is the case, what this generating matrix should look like? A generating matrix will have two parts. One is the parity check matrix and other is the identity matrix. Identity matrix will have k cross k dimension, and the parity check matrix will have k cross n minus k matrix, right? So these are this is the code word, and these are the parity bits, and this will be the message. This is the formation of the code word. Every code word using this type of generating matrix. And this type of generating, if this is the generating matrix, then this type of code will be called as the systematic block code. Now, as an example here, this is the this is my identity matrix. These are my parity bits. And when this is generating matrix for a systematic code, when this is multiplied with the message vector, I will get the code word corresponding to this message bits, right? This message block. So what is the meaning of k tuple? K tuple means in the message vector is of a k elements. N tuple means the code word is of n elements. Again, the same thing is there. Code word vector will be equal to the parity bits and the message bits. Then, because this is how to get these parity bits, right? How will one of the how to get these parity bits? These, because I will have the generating matrix. I will have the how to get the parity bits is that how will you get the first parity bit, which is P1. P1 will be obtained by multiplying M1 with P11, M2 with P12, M1 with P11, M2 with P21, and MK with PK1, right? So this is my first parity bit, right? Second parity bit will come as M1 multiplied with P12, M2 multiplied with P22, and MK multiplied with PK2. So that's what is explained here in the next, that how will you obtain the parity bits from P1 to Pn minus K, right? So systematic code words are sometimes written so that the message bits occupy the left hand, so that I've already explained. So how to generate the code word? This is my message vector. This is my generating matrix for a systematic code. This is parity. This is parity matrix, right? This is the identity matrix. So I will multiply this message vector to this matrix to get the different code words. All right. Plus here means the modulo addition, meaning by the XORing. Then for any, so we will have to, so this is how the code word will be formed and transmitted onto the channel, right? This is how you will perform the linear block coding. This is the way to encode the message data. But at the receiver end, we will have to decode also, because what we will receive at the receiver end, we will receive 6 bits, let's say U1, U2, U3, U4, U5, U6. And we have to decode this code word into 3 bits, which is actually the message vector. So how to decode that? Next slides will explain that. Now this is an important concept. For any linear code, we can find a matrix. So we can always find a matrix H with dimensions n minus k cross n. So what are the dimensions of generating matrix? As I have just explained, the generating matrix will be k cross n, right? So k number of rows will be there and n will be columns. But we can find a matrix H with dimensions n minus k cross n such that its rows are orthogonal to the rows of G, right? And we can prove that multiplication of G with the transpose of H will always be a zero matrix. This is very important condition for orthogonality. And for any linear code, we can find a matrix H with dimensions n minus k cross n such that its rows are orthogonal to the rows of G, right? H is called the parity check matrix and its rows are linearly independent again. So for systematic linear, because H can be generated from G itself. How to generate H from G? Just take the you can use this formula. Write an identity matrix with n minus k dimensions and take the parity check matrix from G and do the transpose, right? So H transpose, because this is H, what will be H transpose? H transpose will be in minus k p. So let me take an example here. So let me show you the G first. This is my G. this is a general kind of G, not the elements are specified. So how many rows are there? K rows are there. How many columns are there? N columns are there. How many parity bits are there in one column? N minus K. How many? What is the size of this identity matrix? K cross K, right? So this is G. How to generate H from G? This is how I can generate H. I n minus K. So I will write. Let me show you how I can generate H transpose from G. H transpose can be generated as this is identity matrix, because this is my here the identity matrix is of dimensions K cross K, but as I said, H will be equal to I n minus K P transpose. So P transpose, so that means H transpose will be equal to I n minus K P. All right. So I will write the identity matrix with the dimension n minus k, and I will take the parity check matrix from here, and I will do the, I will write it like this. Let me show you. This is my parity check matrix, right? P11, P21, PK1. So I take the parity matrix from here and I put it there. So that will be my H. So this, when you multiply the generating matrix with this is actually not H, this is H transpose. So when I multiply G with this matrix, which is H transpose, I will get a zero matrix. That is the condition put on the generating matrix and the parity check matrix, right? So it is easy to verify that. Now, any code word multiplied with this matrix, if you take any code word and multiply the code word with this matrix, because in the code word, how many elements will be there? N elements will be there. So this is my, and this column will have N elements. Now it is easy to verify that the product U H transpose, U is the code word, row vector, which is the code word basically. H transpose is this matrix. Now product of U H transpose of each code word U generated by G and the H transpose matrix yields. So U H transpose, this is code word, this is H transpose matrix. This will always be equal to 0. Where the parity bits P1, P2 up to Pn minus K. Thus, once the parity check matrix H is constructed to fulfill the foregoing orthogonality requirements, we can use it to test. How can I, because I know G will be used to generate the linear block code, to generate the codes, right? So I can form H matrix, parity check matrix from G, and I can also take the H transpose, right? So whenever the code word is transmitted at the receiver, I will receive the code word, and how can I know whether I have received a valid code word or not? What I will do is that I will take that received code word and multiply it with H transpose. The result should come to 0. If it is not coming to 0, then it is not a valid code word. There are some errors introduced by the channel, right? So U is a code word generated by matrix G if and only if UH transpose is equal to 0 matrix. Now there are some important metrics to be understood for every linear block code. Now, for example, if I consider n equal to 6 and k equal to 3, right? How many code words will be there in the code book? 2 raised to the power 3, 8 code words will be there. Actually, in the vector space, how many code words are there? 2 raised to the power 6. But I require only 8 code words to be mapped to the message vector. So how many code words will be there required? Actually, will be 8 code words, right? Now you consider all the code words and try to find out the distance between the code words. What is the meaning of distance? Distance means how many elements are differing from each code word, from one code word to the other code word. How to find the distance between two code words? At every position, you will find out whether it is how many at that position, whether it is differing, whether if it is 1, 1, it is no difference. But if it is 0 and 1, so that means the code word at that particular point is differing. Consider the set of distances between. Hello, Varun. Varun,
हाँ जी सर।
बीच में कनेक्शन ब्रेक हो गया था, है ना?
हाँ जी सर।
So for every code word in the code book, what you will do is that you will find out the distance between the code words. What is the meaning of distance? That if you take two code words with 6 elements each, let's say, then how many bit positions it is differing. The two code words are differing, right? So that will be known as the distance between the two code words. What we will do is that we will try to find out the distance between every pair of code words. The minimum distance out of all these distances, whatever is the minimum distance, so that will be associated as a metric which will be called as the minimum distance of that particular linear code. So that's what is explained here. This minimum distance is very important actually to know that how many errors it can detect and correct, right? So consider the set of distances between all pairs of code words in the space Vn. The smallest member of the set is the minimum distance of the code and is denoted as d minimum. I will explain this. This is actually explaining the weight of the code word. But what I have tried to explain you is that what you will do is that you will find out the distance between each pair of code words for as many code words are present in your code book. So whatever is the minimum distance out of all these code words, that will be called as the minimum distance. Now I will introduce one more metric here. Okay, what is known as the Hamming weight? This distance is called as the Hamming distance, right? And another metric is called the Hamming weight. Hamming weight is actually number of ones in the code word. For example, this is my code word 100101101. So what is the weight of this code word? How many ones are there? Please find out. For example, this is my code word. How many ones are there? 1, 2, 3, 4, 5. 5 ones are there. So that this is the weight of this code word. All right. So let's say two code words are there. What will be the distance between the two code words? At how many bit positions these two code words are differing? So here it is differing, here it is differing, here it is differing, here it is not differing, it is same, differing, same, and here difference. So what is the distance between these two code words? 6. All right. So that is known as the distance. So we will find out the distance between every pair of code words. Whatever is the minimum distance, that will be called as the minimum distance, basically. That will be associated as a metric to that linear block code. Right. So there are two factors I have mentioned here. One is the weight of the code. This is the weight of the code word is 5 here, right? And distance between two code words, I have already explained that how to find out the distance, right? By the properties of modulo addition, we note that the sum of two binary vectors is another vector. So if you do the sum of the two vectors, it will be another vector, right? Whose binary positions are located in those positions in which two vectors differ. So this is differing 1, 0. If you do the modulo addition, this is 1. Again 1. This is 1. So at how many positions you will get 1 here? I will get, by the addition of u plus v, I will get 6 positions. I will get 1. So where I'm getting 1 if I do the modulo addition, that means basically XORing. So 1 XOR with 0 will be 1. So at this point, these two bits are differing. So that is why I'm getting 1. So if these are the two code words, at how many positions I will get once in the addition? I will get 6. So at 6 positions, I will get the ones. So u plus v equal to c. Thus, we observe that the Hamming distance between the two code words is equal to the Hamming weight of their sum. This is very important point which you will be requiring to solve the questions. The point is that Hamming distance between two code words is equal to the Hamming weight of their sum. So distance between the two code words is equal to the weight of their sums, right? So this is the same property that I have explained here, right? Now, the Hamming weight of the vector, the point is that once you will do the addition u plus v, you will get this code word, you will get this result. Now, as I have explained you that only that will be called as a subspace of the vector space, where the result of the addition of any two code words will also be another code word, right? But if you look at the addition, the weight of this uh, code word, this will also be another code word, because the addition of the two vectors will generate another code word in the same subspace. So that means, and this addition is giving what? This addition is giving us the distance between the two code vectors. Just hold for 1 minute. Okay, so what is the distance between these two code words? Distance is, if you do the modulo addition, right? So that will actually be another code word in the same code book. So what is the meaning? Meaning by what is the weight of this addition? Weight is 6. What is this? How this vector has come? By the addition of these two vectors. Addition of these two vectors means it is giving us the distance between the two code vectors. Number of ones that we will get in the addition of the two vectors is actually the distance between these two vectors. But number of ones in this vector is actually the weight of this this addition, u plus v. So that's what is said here. Distance between the two vectors is actually weight of u plus v. So what we can do is that let me show you in the screen. Yeah. The Hamming weight of the U vector is denoted as the number of non-zero element. That means 1. We are not considering any other element. We are considering only zeros and ones. The Hamming distance between two code vectors is actually the weight of the addition, right? Uh, the point that I want to make here is that instead of finding the, if you, let us say, if you want to find out the minimum distance of a linear block code, what you will do is that, let us say there are 50 code words in the code book. So if I ask you to find out the minimum distance of this code, what you are supposed to do, actually you are supposed to calculate the distance between each pair of code words. So you can well imagine how many combinations you will have to check. If there are 50, then every code word will be checked with other 49, and so it will be a huge task to perform. But one simple method is there. What you do is that you find out the weight of each code word, right? So minimum weight is actually minimum distance. So that's the point that I want to mention here, because the background behind that is that if you add two code words, then the resultant will also be a code word in the same code book, and which is so. And I also found out that the distance between the two code words is actually the weight of the resultant code word. So if you elaborate this concept, this can be taken as the minimum weight of the code words is actually the minimum distance of the minimum distance of that code. All right. So this point you will understand once you will try to solve the numericals given in the. So actually, this minimum distance is directly related to the error detection and the correction capability of a code. So how many errors you can detect? D minimum minus 1. These many. Please take this point straight away. I will explain how this formula has come maybe in the other classes. So please take this point straight away to make the things clear. The number of errors that can be detected by a particular linear block code is given by d minimum minus 1. Number of errors it can correct. Error correcting capability of a code is given by d minimum minus 1 and take its floor. That means the lower integer. Take the floor value d minimum minus 1 divided by 2 and take the floor value. So whatever is the minimum distance of a code minus 1 divided by 2. So these many errors the particular code can correct. And how many it can detect? D minimum minus 1. Now at the receiver, let us say you receive a vector r, which may be a corrupted vector. How will you come to know that it is a corrupt vector? If you multiply r with h transpose, so that will not be equal to 0. So if that is not equal to 0, that means this is not a valid code word. But I can represent the received vector with the transmitted vector plus the error vector, some error pattern. R is equal to how many r, r1 r2, so number of elements will be n again. This is the received code vector, but some error vector will also be added into the transmitted vector to, so from there the received vector has been generated, right? So this is my received vector. In this block diagram, it is the received vector. This was transmitted vector, but some error vector was added into the transmitted vector. So I got a corrupted received vector. So how to correct and how to detect the errors? There is a procedure called syndrome testing. So S is the syndrome of R. S is another vector which will be called as the syndrome of R, which is the received vector, corresponding to the error pattern E, corresponding to this error pattern E. So how to calculate this syndrome? Syndrome will be calculated as S equal to RH transpose. R is the received vector, H transpose is the parity transpose of the parity check matrix. This is basically equal to EH transpose. Why it is equal to EH transpose? Because you, if I substitute the value of R here, it is U plus E. So U multiplied with H transpose is actually equal to 0. So if you do the received vector multiplication with the parity check matrix transpose, or if you do the error pattern with H transpose, it is the same thing. Both the multiplications will give you the syndrome of R, right? So there will be a procedure called syndrome testing. Let R be the received vector resulting from the transmission of U. So we can therefore we can therefore describe R as R equal to U plus E. E is an error pattern or error vector. So the syndrome of R is defined as capital S is equal to RH transpose. I have already explained in the previous slide. The syndrome is the result of the parity check performed on R. So R is the received vector. We will try to perform a parity check on the received vector, whether it is a valid code word or not. So to determine whether R is a valid member of the code word set or not. If in fact R is a member, the syndrome S will have a 0 value, will have a value 0. The syndrome vector will have all 0 elements. If R contains detectable errors, but if R is an error and it contains detectable errors, the syndrome has some non-zero value. If R contains correctable errors, the syndrome has some non-zero value that can earmark the particular error pattern. Now S is equal to U plus E, because what we are performing is R into H transpose. So UH transpose is actually equal to 0 for all members of the code word set. So syndrome testing can be performed equal to EH transpose also with the error pattern. Now this equation is evidence that the syndrome test, whether performed on either a corrupted code word or on the error pattern that caused it, yields the same syndrome. An important property of linear block codes is fundamental to the decoding process is that the mapping between correctable error patterns and the syndromes is 1-to-1. So these are some characteristics of the edge. It is interesting to note the following two required properties of the parity check matrix. No column of H can be all zeros, or else an error in the corresponding code word position would not affect the syndrome and would be undetectable. All columns of H must be unique. If two columns of H were identical, errors in these two corresponding code word positions will be indistinguishable. So these are some characteristics of parity check matrix. Now, suppose that the code word transmitted was 10110 and the received code word is 00110. So that means if you look at U and R, the first bit is changed. So that means due to error, the received vector is 0 here at the first position because of noise or whatever reasons. So this received vector is in error. If we want to check whether this received vector is a valid code word or not, what we will do, we will try to find out the syndrome. Syndrome is given by RS transpose H, because I know G, right? G will be given to you. I know G, I can find out H transpose. If I multiply the received vector with H transpose, what I'm getting here is 100. Syndrome is not 0. So that means the received vector is not a valid code word. What actually was transmitted is not, this is not what actually was transmitted. Rather, this is not a valid code word from the code book. So next, we verify that the syndrome of the corrupted vector is the same as the syndrome of the error pattern. So what is the error pattern? If I take the error pattern as 1000, so what I am finding is the syndrome is 100. Once I have found out the syndrome, right, I can have a table which is syndrome error. Now my syndrome is 100, so correspondingly I can find out the error 1000, because if I do EH transpose or RH transpose, the syndrome will be same. So if I am finding the syndrome here, which is 100, and correspondingly, if I find out the error pattern, now error pattern will of course be same because it is giving the same syndrome. This error pattern is what? 10000. So it is telling me at the first position, the bit is in error. What I will do at the receiver, I will just change this bit to 1. And I will get the received corrupted code word decoded as 10110. So what I'm supposed to do is that I need to find out the syndrome. So once I have found out the syndrome, I will correspondingly I will find out the error pattern. All right. Now we have detected a single error and have shown that syndrome test performed on either the corrupted code word or on the error pattern that caused it yields the same syndrome. This should be a clue that we not only can detect the error, but since there is a one-to-one correspondence between error patterns and the syndromes, we can correct such error patterns. Right? Let us arrange the 2 raised to the power n. So how many code words are there total? Let us arrange the 2 raised to the power n tuples that represent possible received vector. So what we will do is that actually we will form a standard array. Now how the array is formed? Such that the first row contains all the code words, starting with all zeros code word. So let me show you. This is the standard array. First row is all the valid code words. How many code words should be there? 2 raised to the power k. Starting from U1 to U2 raised to the power k, these are the valid code words. The first code word is all zeros code word, right? So that's what is said here. Let's arrange the 2 raised to the power n tuples that represent possible in a standard array such that the first row contains all the code words starting with the all zeros code word. So U1 in this diagram, this is my all zeros code word, and first row contains all the valid code words, right? And the first column contains all the correctable error patterns. Please understand this. The first column will contain all the correctable error. Please mind it, if you design a code, right? Not every error, error pattern or not every corrupted received vector can be corrected. If you define the error pattern, few error patterns can be corrected. How many error patterns can be corrected? E raised to the power e subscript 2 raised to the power n minus k error patterns can be corrected. All right. So recall from the basic properties of linear codes that all zeros vector must be a member of the code word set. This is very important point. Each row will be called as a coset. Each row in the standard array will be called as a coset, right? consists of an error pattern in the first column. The first column will contain the error pattern because this U1 is an all zeros code word. It is equal to the error pattern also. Error pattern means there is no error. All zeros will be, there will be no error, right? And each row is called a coset, consists of an error pattern in the first column called the error pattern. So the first column will be called as the coset leader. Each row is called as a coset. Each first column is called as the elements of the first column will be called as the coset leaders, right? Each row called a coset consists of an error pattern in the first column called the coset leader. So the first column will be called as the coset leader, followed by the code words perturbed by the error pattern. So what are these code words? This is, if this is the error pattern, so this code word will be U2 plus E2. That means U2 was corrupted by E2. This is the error pattern. So that's how the whole standard array is formed. The standard array format of an n, k code is as follows. Note that code word U1 is an all zeros code word, plays two roles. It is one of the code word also, and it can also be thought of as an error pattern, E1 here, right? The pattern that represents no error such that R equal to U. The array contains all 2 raised to the power n. The array contains all the code, all the possible full vector space, 2 raised to the power n tuples in the space Vn. Each n tuple appears in only one location, none are missing and none are replicated. Each coset consists of 2 raised to the power k n tuples. So coset means every row. So therefore, there are how many cosets? Every row will be called as a coset. How many rows will be there? 2 raised to the power n divided by 2 raised to the power k. 2 raised to the power n minus k cosets will be there, as is shown in this in this diagram. Now, the decoding algorithm calls for replacing a corrupted vector, right? Any n tuple excluding those in the first row with a valid code word. So whatever you will receive, if it is a corrupted vector, you will have to correspondingly, let us say, let me explain this point. Let us say you receive this vector. This vector is a corrupted vector. So I will have to replace this vector with this valid code word, which is U2. That's what is said here. The decoding algorithm calls for replacing a corrupted vector with a valid code word from the top of the column containing the corrupted vector. Suppose that a code word is transmitted over a noisy channel, resulting in a received vector ui plus ej. If the error pattern ej caused by the channel is a coset leader, if the error pattern is a coset leader where the index j equal to 1 to 2 raised to the power n minus, the received vector will be decoded correctly into the transmitted code word ui. If the error pattern is not a coset leader, then an erroneous decoding will result, and we will not be able to decode that part. What is the meaning here? Only these error patterns we can decode. If any error other than these patterns occur, then we will not be able to decode it correctly. So any linear block code with its capability cannot correct every error pattern. So that's the point here. Then the syndrome of a coset. If AJ is the coset leader or error pattern of the jth coset, then UI plus EJ is an n tuple in this coset. So the syndrome of this will be given. So we will find out the syndrome, right? Since this is equal to 0, my syndrome will be equal to EJH transpose. The name coset actually has, this is the same thing as I have already explained. Coset means a set of numbers having a common feature. What is the common feature in a coset? The common feature is the this error pattern. This error pattern is common throughout this row. So that is what that is why it is called a coset, a set of numbers having a common feature. What do the members of any row have in common? It is clear that each member of a coset has the same syndrome, right? The syndrome for each coset is different from that of any other. So it is the syndrome that is used to estimate the error pattern. And this is the procedure, how to do the decoding. The procedure for error correction decoding proceeds as follows. Calculate the syndrome. For any received vector, what we will do is we will calculate the syndrome, locate the coset leader. That means find out the error pattern whose syndrome equals to RS transpose. This error pattern is assumed to be corruption caused by the channel. The corrected received vector is identified as U equal to, how to find out the corrected code word? You just add R plus EJ. You just do the modulo addition of the received vector with the error pattern that you have found out. We can say that we will retrieve the valid code word by subtract. Actually, it will be basically the subtracting out the identified error. In modulo 2 arithmetic, the operation of subtraction is identical to that of the addition. So that's how the this is standard. Some more slides on standard array. Same thing, right? This is the transmitted vector. Let's say this is the received vector. You will find out the syndrome. So once you find out the syndrome in this table, the syndrome found out is 100. So what is the error pattern I need to find out? For 100 syndrome, this is the error pattern. Now what this error pattern says, the first bit is in error. So in the received vector, what I will do is that I will change the first bit. If it is 0, I will make it as 1. If it is 1, I will make it as 0. Since this is 0, I will make it as 1. So that means this is my actual code word that was transmitted. So this is the theory and the background of the linear block codes that you are supposed to do in a very, thorough manner. I have also given you one assignment based on linear block codes. Please try to solve the questions given in assignment number 2, and please ask if any doubts you face, because you will find questions from this chapter in your final examination. All right. If any questions are there at this moment, you can ask, or maybe at the later stage, you can also ask the questions. Thank you for joining. Thank you.